So in this video we're going to go over powers of matrices. So powers of matrices, let A be a square matrix. So this is important. Notice it says square matrix. So this definition is only for square matrices. And we're going to let R and S be non-negative integers. So non-negative integers. So we're talking 0, 1, 2, 3, like that. So property 1 says if A to the R times A to the, if you have a matrix A to the R times the same matrix A to the S, then you get A to the R plus S. So this should look like a typical exponent rule that you're accustomed to using with real numbers. And a justification for that would be simply to identify that if we have non-negative integers, these are really counting numbers. So if we have A to the R times A to the S, this A to the R means multiply A times itself times ... times itself, and you would be multiplying it by itself R times. And then times, you would be doing A times itself, A times times A. You'd be multiplying A by itself another S times. And so altogether you see that you would get R copies of A and S copies of A would tell us that we had A to the R plus S copies of A being multiplied. The next rule down should look similar, a power being raised to a power. We get the product of the powers for the exponent, so similar to exponent rules that you've already learned. And the justification would be to go A to the R to the S, and because we have non-negative integers, we can count what's going on. So we would get A to the R times A to the R times ... times A to the R, and you would get S copies of this, S times. And then, that's a horrible S. And then, using this property number 1, you would see that you would just get R plus R plus R plus R. You would get R plus R plus, let's go ... plus R. But you would get S of them. So it would be S of them. And if you have S R's, then you count them just by using multiplication, R times S of them. And here, this should look similar to an exponent rule you already know. So for example, we know that if we have an eligible base A being raised to the 0 power, if it's a real number, we know this equals 1. So for example, 10 to the 0 equals 1. And what we want to recognize is that when we raise the number 10 to the 0, what we get is a 1, but we know that 1 is called the multiplicative identity. So what we want to think of, the way that we want to think about raising a real number to the 0 is that we're really raising the real number to the additive identity. And when we raise a real number to the additive identity, the result is the multiplicative identity. So here we're taking and raising a matrix A to the 0, and we're defining this if this is a square matrix or an n by n square matrix, then we're saying, hey, if we raise a matrix A to the 0, the 0th power, then we're going to get the identity matrix, the n by n identity matrix. And remember, the identity matrix was the diagonal matrix whose diagonal has all 1s in it, and all the other entries off the diagonal, because it's a diagonal matrix, are 0s. So these should look similar to the exponent rules that you are already familiar with. And then we can use the exponent rules to do some basic computations. So for example, we could recognize that if we have A to the 4th, we could rewrite it as A to the 2 times 2, which is the same as A squared using exponent rule or property number 2 right here. So if I wanted to calculate A to the 4th, I could do A times A times A times A. So I'd have to take one product 2 products, 3 products. Or we can use this property to shorten the process so that we only have to take 2 products. We do a squared times, we can do a squared times a squared. So we have to do a product once to get a squared, and then a squared times a squared is a second product. So we can shorten the computation. So a squared is going to equal 1, negative 1, negative 2, 0 times itself. 1, negative 1, negative 2, 0. And then this is a 2 by 2 times a 2 by 2 is going to generate a 2 by 2. So the dot product of row 1 with column 2 is 1 times 1 plus negative 2 times negative 1 is 2. And then row 2, column 2, we get 1 times negative 2 is negative 2 plus negative 2 times 0 is 0. And then we get negative 1. Now we're working on row 2, column 1. So we take the dot product of row 2 with column 1. Negative 1 times 1 is negative 1 plus 0 times negative 1 is 0. And then we get negative 1 times negative 2 is 2 plus 0 times 0 is 0. And then we can simplify those entries. So we get 3, negative 1, negative 2, 2. And this is a squared, so to get a to the 4th, we just multiply a squared times a squared, which will be a to the 4th. So we get 3, negative 1, negative 2, 2. And by doing it this way, we save one product. We have to do one calculation, product calculation less by doing it this way. So we get row 1, column 1, 3 times 3 is 9. Plus negative 2 times negative 1 is 2. Row 1, column 2, 3 times negative 2 is negative 6, plus negative 2 times 2 is negative 4. And then we get row 2, column 1 to get the row 2, column 1 entry. So we get the dot product of the row vector with the column vector. Negative 2 times 3 is negative 3, plus 2 times negative 1 is negative 2. And then negative 1 times negative 2 is 2, plus 2 times 2 is 4, and then simplify that. So we get 11, negative 10, negative 5, and 6. And then the final question is, to wrap this up, it says, if a matrix is not a square matrix, can you raise it to a non-negative integer power? And the answer is no. So let's say we have a matrix A and it's a 3 by 2 matrix. So the problem is if we tried to calculate A squared, we would get A times A, but this would be a 3 by 2 times a 3 by 2, and these inner numbers wouldn't match. We wouldn't have the same number of columns as we have rows, so the column and row the row vectors and the column vectors won't have the same number of entries, then we won't be able to take the dot product. The dot product won't be defined. So if m does not equal n, then you can't raise a to a non-negative integer power, because when you do that, you get m by n, and these inner numbers don't match. So these powers are only defined for square matrices.